Hi everyone, this is section 9.3 on geometric sequences, partial sums, and series. Now with arithmetic sequences, we took the initial term and then we kept adding the same number over and over again, the common difference. Take a wild guess what's happening here. Let's see, 2 to 6, 2 to 6, 6 to 18, 18 to 54. Here we're multiplying by the same number over and over again. Here, 3, which is called the common ratio, not the common difference. Because 6 over 2 is 3, 18 over 6 is 3, and so forth. Here we begin with 2. After that, we successively multiply by 3 to obtain the other terms. Unlike for an arithmetic sequences where we added, here we're successively multiplying by 3. So a geometric sequence is determined by its initial term. We normally start with a sub 1, which is 2 here, right? Let's see here. Okay, so common ratio, denoted by R. Okay, the second term divided by the first term, or the third term divided by the second term, and so forth. Here, R was 3. So again, you could either do 6 divided by 2, that's 3. 18 divided by 6, that's 3. 54 divided by 18, that's 3, and so forth. Now, here you might be going, oh, well, why would I need to do that? Bear in mind, these numbers could get very ugly. They can become ugly fractions. So it may not be obvious what the common ratio is just by looking here. You might have to actually have to work it out, like this over this, or this over this. We have a choice. And sometimes something like this over this might be easier than this over this. For example, maybe this thing is a hideous fraction. Okay, so the following information completely determines our sequence. The sequence is geometric. The initial term is a sub 1, which is 2. Common ratio R is 3. Then in principle, you can get any term in the sequence. But it might take a while, for now. The recursive definition, you start with a sub 1, usually, that's given. Not always, but often it's given. To get the next term, you take the current term, and you multiply by R, the common ratio. To get term number k plus 1, you take term number k, multiply by R. It's like dominoes, which we'll talk about later. Here's term k. Here's term k plus 1. To get from 1 to the next, multiply by R. By the way, we assume that these are non-zero for now. Otherwise, it gets kind of tricky, right? Because let's say you start with 4, right? Then it's 0, 0, 0, 0. Is that really geometric if R is 0? No, that's kind of weird. All right. So for example, this sequence here is completely defined by the fact it's geometric. A sub 1 is 2, R is 3. Okay, the formula for the general nth term of a geometric sequence. Let's start with, it's similar to what we did for the arithmetic, except here, instead of adding D step by step, we're multiplying by R. So we have a sub 1 equals a sub 1. Okay, a sub 2, how do we get that? It's a sub 1 times R. To get a sub 3, remember, a sub 3 is, by the recursive definition, a sub 2 times R. A sub 2 is a sub 1 times R. Plug this in for here. And you get a sub 1 times R, and then this guy is times R. So we get a sub 1 times R squared. A sub 1 times R squared. So to get from the first term to the nth term, you don't multiply by R n times, but n minus 1 times. Here, we multiply by R twice. To get the third term, we multiply by R twice. A sub 4 is a sub 1 times R cubed. Again, using my step analogy from before, if you're going from the first step of a ladder or staircase to the fourth step of a ladder or staircase, okay, how many steps do you actually take if you go step by step? Well, 1, 2, 3. Again, it's that computer science issue. You got to be careful. So in general, to get from the first term to the nth term, it's a sub n equals a sub 1 times r to the n minus 1, because you multiply by r n minus 1 times, and that's exponentiation. For example, here, r squared means that you multiply r times r, right? You multiply 2 copies of r. Again, the general nth term of a geometric sequence with initial term a sub 1 and common ratio r is given by this. Remember it, or figure it out. Now, this represents a discretization of an exponential function. And notice we have n and an exponent here. If these are numbers, right, we consider these as basically constants or numbers that we find, right? We end up having an exponential function in n, okay? Maybe a discretization of that, right? A sequence. In fact, when we did the card sharks example, remember Norma, the game show player on Card Sharks, when you had to turn 7 cards, right? And she won $28,800. We modeled it with a smooth J curve, but actually, technically, it was dots. It was a geometric sequence because, it's, flip a card, flip a card, flip a card. It's a discrete scenario, not a continuous scenario. By the way, there was a $200 bump in the middle, but we're ignoring that for now. Okay, this is like card sharks. This is really the card sharks situation. Okay, it's not so much a smooth continuous exponential function. It's more a discretization of that. It's really a geometric sequence, really. So if you say that the value of a house increases by 2% per year, and you're reassessing it every January 2nd, then you're really talking a geometric sequence. All right. So geometric sequences often arise from exponential models, like for compound interest, population growth, and unfortunately, coronavirus growth, right? If you want to track week by week, for example. Okay, example, find the 6th term of this geometric sequence. Although this you could do brute force, boom, 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 all right? I guess we can check our work that way. Assume that 2 is the first term, a sub 1. So we're given a sub 1, we have to find a sub 6. Okay. A sub 1 is 2. And what's the common ratio? All right. Now, so here, this is an example. If I were to ask you what's the common ratio, you might go, wow, here, it's not as clear as before. But think clearly, think logically. You can go a sub 2 over a sub 1. What's that? It's going to be negative 1/2. Or perhaps even easier, look at this. A sub 3 over a sub 2, 1/2 over negative 1. Well, that's negative 1/2. That's even easier. All right. So then here's our general nth term formula for a geometric sequence. We want the 6th term, so we plug in n equals 6. All right. We know that the first term is 2. We know the common ratio is negative 1/2. Or we figured it out, right? To the 6 minus 1. Okay. So to the 5th. This power here is negative 1 over 32. Multiply in the 2, you get negative 1/16. Now, you don't have to check, but it might make us feel better if maybe brute force, right? Remember, this is the common ratio. What's 1/2 times negative 1/2? 1/2 times negative 1/2. It's negative 1/4. What's negative 1/4 times negative 1/2? Negative 1/4 times negative 1/2 is positive 1/8. And lo and behold, what is 1/8 times negative 1/2? It's negative 1/16, which verifies what we had here. And certainly, if I ask you for the 100th term, then you're going to want to use this formula. Although, if I were to ask you for the 100th term, then you might want to leave exponents in your final answer because you could have very ugly pieces. Now, incidentally, as n approaches infinity, what do these terms seem to approach? If you keep going on and on and on, and you multiply by negative 1/2, what seems to be happening? They're approaching 0. They seem to be approaching 0, and they do. When does that happen? When do the terms of a geometric sequence or series approach 0? That happens if and only if r is strictly between -1 and +1. So if r is -1/2, like here, or +1/2, okay, or another way of putting it, the absolute value of r is less than 1. Okay, so these terms approach 0 if and only if the absolute value of r is less than 1. If r, the common ratio, is strictly between -1 and 1, like -1/2, +1/2, 0.99, -0.99, then the terms will approach 0. If r is 0.99, it might take a while for it to really get close to 0, but yes, it'll approach 0. Imagine that you have a store and it cuts prices 1% every week, right? Then eventually things will be very cheap. Okay. Now, don't worry about this. The formula for the nth partial sum of a geometric sequence, but it's the sum of the first n terms, basically. You don't have to know this formula. Now, you do have to understand the concept of an nth partial sum, the idea of adding the first n terms, the cumulative sum. But you don't have to know this particular formula. Oh, good. So we get to kind of skip over this stuff. Good. Oh, good. Look at this. All right. All right. Next up, this will be fascinating. And these are extremely important in Calc 2, Math 151, infinite geometric series. Okay. I mean, finite series aren't so interesting. And why didn't we care so much about infinite arithmetic series? We'll see next time.